Mhm. Yeah, the magnetosphere is basically what results from the Earth's magnetic field. And if you really just sort of look at it at a first look, you would think the Earth's magnetic field is kind of like a dipole. You know, you put a a dipole on a table and put some iron filings around it, and it looks like a dipole around, you know. Now, the Earth's magnetosphere doesn't quite look like that, and the reason for that is that there are particles coming from the sun, you know, together with magnetic field. They're coming with very high velocities, you know, millions of kilometers per second, or miles per second, I guess it is. And they hit the magnetosphere, and they compress this magnetic field on the side that is facing the sun, and they extend it into a very long tail on the night side. Yeah? And as a result of that, it's not just a simple dipole magnetic field, it's something that looks much more complicated, and it has electrical currents flowing inside it. Particles get accelerated inside it to very large energies, like tens or hundreds of thousands of volts, in some cases even millions of volts of energy that you can obtain because of these changes that are driven by the interaction with the wind from the sun that we call the solar wind. Originally, I became interested in this because it was nicely mathematical. There was lots of math. And now everybody says, ooh, okay. Well, it's just I kind of liked it that way. So I originally did a lot of math stuff, but then as I kind of grew older and got my PhD, and then I came to the US. I'm from Germany originally. I started to learn how to do computer simulations. And with computer simulations, you can look at things and turn it around and see how it evolves and so on. So I became much more interested in seeing how things behave other than just writing down equations, you know, how they should behave. And that's kind of the thing, how things evolved. You know, the more I did of that, the more I liked it. And then this space weather came along, and you know, with these calculations, you can calculate what happens, and you can try to predict what happens, and you can visualize it. You can spin it around until you get dizzy, you know, but you can also try to really get some science out of it. And that's kind of how it evolved in a very short nutshell here. I think space itself is something really cool. I mean, you can go out, humans want to go out there, you know, we rely on space in so many ways. There's so many interesting things going on there. There's a lot of really nice research to be done, and neat things to be found out. And we now have tools and capabilities that we have sort of developed over the years to start to model this, and to not only understand it, but also use understanding then to predict it. So we are just getting there. We're moving into that area. We're nowhere near where the weather prediction is, you know, but we're working. You know, we got to keep working at it. And I mean, it's extremely gratifying if you're able to push the barrier forward just a little bit. You find out something new. You know, you use it to predict something, and you're not only doing this for the sake of, you know, developing cool understanding. Not that is bad, you know, but it is also for it's actually something for humanity. You know, you're in this luxurious position to say, well, I'm doing something in space, but it actually helps somebody, you know. And that's what I find so exciting. And I think really that has a lot of can have a lot of attraction to children. So I would encourage them to really think about this and try to stay abreast. I mean, there's so many things going on now, like NASA's stereo mission. You can see the sun, you know, all the source of all these things in stereo, how things evolve. I just saw that just the other week, and it's phenomenal. Yeah? So I can highly recommend it. I am sold on it. And I think lots more people could.